Welcome to the Explainer. Today we're pulling back the curtain on the hidden data that makes every single video you stream possible. We're going to explore how this data, which was first designed just to be efficient, is now giving AI a totally revolutionary way to understand our world.
You know, when you watch a video, it feels like you're just seeing a ton of still images flashing by one after another. But what if I told you the most important information isn't in the pictures themselves, but actually in the gaps between them? Let's dive into how understanding that in-between space is making video analysis for AI incredibly fast and efficient.
Okay, let's get right into it. We're going to start with a really simple question about something that's fundamental to all digital video. Think of it as finding the anchors in this huge, constantly flowing sea of pixels.
So here it is. How many keyframes are in a typical YouTube video? Now this might seem like a kind of random question, but the answer really gets to the heart of how videos are built for maximum efficiency. So first things first, what exactly is a keyframe?
A keyframe, or an iframe, is the only frame in a segment of video that's a complete standalone picture. It doesn't need any other information to show up on your screen. Everything else you see is basically built around these key visual milestones.
So for a massive platform like YouTube, the answer is about every 2 seconds. Yep, they typically place one of these full-picture keyframes at that interval. It's this surprisingly consistent rhythm that strikes a perfect balance between video quality and data efficiency.
And this just shows you how predictable it all becomes. Once you know that 2-second rule, you can pretty much estimate the keyframe count for any video. A 10-minute video has around 300 keyframes. An hour-long one has about 1,800. And this isn't just fun trivia. This establishes a real baseline for how we can start analyzing video content in a much smarter way.
Okay, so if the keyframes are the big, important anchor points, what about all those thousands of other frames that are squeezed in between? What are they doing, and what kind of story are they telling?
Well, this is where things get really clever. The frames between the keyframes, the P frames and B frames, they don't store the whole picture all over again. They're way more efficient. P frames just describe what's changed from the frame that came before it, and B frames are even smarter. They can look both backward and forward to describe changes even more efficiently. And how do they describe that change? With something called a motion vector. Just think of it as a tiny arrow that says, hey, this block of pixels from the last frame, it moved over here. These little vectors are the secret sauce, describing all the action without having to redraw the entire scene every single time.
So this is the crucial point, right? If this motion data is so useful, can we just grab it and use it? Well, as it turns out, getting your hands on this incredibly rich motion data, it isn't always that straightforward.
The challenge often comes down to the codec. You can think of it as the language the video is written in. For common codecs like H.264, yeah, you can pull this data out with standard tools. But for the advanced codecs that YouTube loves to use, like VP9 or AV1, it's actually much harder. You need specialized software just to get to that valuable motion vector data.
Okay, now let's see how this all builds into something really powerful. Because if we can get past that hurdle of accessing the motion vectors, we can create a groundbreaking, hyper-efficient method for AI video analysis.
So why would anyone bother with all this complexity? Well, the answer is that by combining these two things, the full pictures from keyframes and the pure motion data from vectors, we can create an incredibly compact yet information-rich signal that is just perfect for AI systems.
And the data savings are just staggering. I mean, look at this. If analyzing every single frame is 100% of the data, just using the keyframes gets you all the way down to about 5%. But then you add in the motion vectors and you're still only at about 10% of the original data size. That's a 90% reduction. Just think what that means for a self-driving car analyzing the road, or a platform trying to moderate millions of hours of video. Less data means faster, cheaper, and more scalable analysis.
This approach really is the sweet spot. Using just keyframes saves a ton of data, but you lose all the information about motion. Using all the frames preserves everything, sure, but it's a massive amount of data. Combining keyframes with motion vectors, though, that's the genius move. You dramatically cut the data size while preserving both the critical visual context and the essential motion information.
So the process itself is beautifully simple. First, you pull out the keyframes to see what is in the scene. Second, you extract the most important motion vectors to see how things are moving. And finally, you feed that compact, combined data stream to an AI. It gets a rich understanding of the scene without being overwhelmed by tons of redundant pixel data.
So, the bottom line is this. We're teaching AI to be more efficient by giving it the same compressed information that video codecs have used for years. We're moving beyond just feeding it endless pictures and instead giving it the core components of sight and motion.
This technique is a complete game changer for understanding actions, events, and dynamics in video. By rethinking the very data we feed our AI systems, we're unlocking incredible new possibilities for how machines will perceive, interact with, and ultimately understand our world. The question isn't just what comes next, but what actions will AI be able to recognize that were once completely invisible to it?